Hello, everyone, and welcome for joining the Apache Pinot Contributors Core, number two. So for this core, we are mainly working on like with the Apache Pinot contributors, developers, to like showcase how as a committer and the PMC, what we are doing and how we are developing, reviewing code and all those kind of things will be like a serious kind of talks and the events. At the very beginning, kind of series, we're just talking about all the basics and also like some very simple, easy kind of starting point for like getting the code or contributions to Pinot. So, okay, so here we are going to start our session for today. Today we will have two sessions. The first one is from me. It's about building your own kind of UDFs in Apache Pinot. And the second one will be by will be given by Yash. It's talking about how to optimize the queries in the Apache Pinot. Yeah. Also, like as Robert mentioned, feel free to drop any questions, and we'll be trying to like answer it either like during the talk or we can answer it after. Okay, so let's get started, and also let me share my screen. So, my talk today is about getting started with the UDFs in Apache Pinot. The agenda is pretty simple. It's like I'm just doing a very quick intro of what's the UDFs, and then going through a simple example of how to write a UDF, and we do some live demo and uh, over the like code walkthrough and the live demo. I will say like certain things like our best practices, and then it's QA. So yeah, let's just go faster. So what is UDF? UDF is pretty much like the customer functions in SQL, and because for every company, every use cases, people may have their specific kind of like requirement other than the built-in kind of like SQL functions. So this kind of UDF capability allows users or customers to actually extend Pinot and be able to like deploy Pinot in their way. Uh, we have like in Pinot side, we have like three types of the UDFs. One is called the scalar functions. This is like what I will talk about mainly today. This is like where we have a majority of our customizations and the kind of like ease of use and also like allow users to do all those kind of like simple implementation. And it's also very super lightweight and very easy to get plugged into Pinot. Second one is about transform functions. This is also like one-to-one mapping. It's like scalar function and the transform function. Functionality-wise, it's like same. It's like if you do like one plus one or like add functions, it's always like converting from one row to another row, right? This is called a one-to-one mapping. Scalar function is like the implementation of like how I can transfer one row's value into another. Meanwhile, the transform functions allows more optimization. Internally, it's like doing everything in batches so that it will allow users to do further optimization and gain like more speed in terms of like query kind of efficiency. However, both transform function and aggregation functions, they all require the Pinot repo code change. Instead of like scalar functions, people just need to do something like their own kind of code module build and then drop the jar. So for the scalar functions, it's very simple. This is like just doing like one-to-one functional mapping. And in Pinot SPI, Pinot SPI kind of like a module, we define some class, some annotation called scalar functions, a scalar function. And if you just annotate a function called scalar function, and also when you implement it, you put this function under this package org.apache.pinot.common.function.scalar. Then this thing will be automatically loaded if the jar or whatever things is in your class path. Here, I'll just do a very quick and simple demo of this kind of implementation. Basically, it's like just write a UDF and build it, and then copy the jar to a Pinot distribution, and then restart Pinot. So here, let me stop share and share my whole screen. Okay. Here I have one like demo kind of environment. And I need to remove this. Okay, so here, this is like just a Pinot 1.3 kind of like a release. And I'll just run something called a quick start batch. This is like a very simple way and like one command to bring up all the Pinot component. This is like also very easy to test everything with Pinot. And apart from that, let's just go to this like Pinot Pixart, and I will also show you uh, here. This is like my repo I just shared here. So this repo is already a public repo, and you can refer to it very easily. So here is like a very simple code repo. Oh, here is easier. So it's like a very simple. I just add three functions. One is related to like a compute
Hey,
two
Xiang,
strings. Just hello,
could you increase the font size?
font size. Ah, okay. Well, too much. Okay. Uh, yeah. Okay. Here is like very simple. If you look at here, for my implementation, I have one, I just have like one package called org Apache Pinot common function scalar. Everything you want to like define as scalar functions right here, write it under this package. And here, I use this annotation called the scalar. Right, this is a scalar function annotation. If you put this annotation, then Pinot will know, okay, for this function under this package, I will try to load it automatically when you start Pinot. And here you can give some names or alias of the functions if you would. And here I just define a very simple functions to one is to compute this like length chain kind of distance. One is to do like strip function from a string, and the third one is like compute something called a sigmoid of some number, right? So here, if we go to this kind of like repo, right? So if I do, let's say, sigmoid on just some random number, if you just run the query, you will see error, right? So you will say, oh, there's an unsupported function called the sigmoid, right? So here, again, I will just quit this one, and here, very simple, right? This is your code, and here is the POM file. For this POM file, I specifically mentioned to do like Java 21 because I built everything with Java 21. But if you are using other Java version, you can feel free to modify here. And here I use Pinot version 1.3. One thing to be mentioned here is like for all the Pinot dependencies, you make those scope called provided. The reason here is like when you try to build this jar, you don't really want to repackage all those Pinot libraries into the shaded jar because you are anyway running this jar inside the Pinot class path. So all those kind of like Pinot dependencies are already there. So you don't need to like uh, uh, include those jars in your shaded jar. After this one, you just run one very simple command, just run maven clean package. So this will try to build these two jars. I, it's gone. This is the Java. Yeah. After the build, you will see there are two jars. If I show this target, you will see these two jars. So this original Pinot UDF jars is like just the uh, all the class file inside this jar within the repo. It should be just like one of this my function.java. Uh, yeah, it's like everything related to this project only. And this Pinot UDF example 1.0 snapshot jar is actually the kind of like the shitty jar. And from here, I'm just let me also from here I create one directory called the Pinot UDFs under the plugins directory. So and then I copy this Pinot UDF example 1.0 snapshot jar into this UDF directory. And afterwards, I'll try to rerun this quick start. If I go to this Apache Pinot, sorry, right, this is like pretty much the binary you're downloading from the official website. And if you find this like plugins, you'll see like all the Pinot plugins here, and you just create one directory because when you start Pinot, Pinot will try to load all the jars under this plugins directory. And if you just create some directory and drop the jar, Pinot will automatically load this jar during the start. So yeah, if you look at here, this one is like the quick start is loading. So I think I should be able to run this query again, right? So see now this is for the airtime, this kind of function is already been running. So it's like fairly simple to run, I mean to build your own kind of scalar function to do all those like one-to-one mapping from your for the code perspective. And this is like a very simple live demo and what I can show for today. And the next thing I'm going to talk about is about the transform functions. This is like a bit more complicated because you need to really modify the Pinot code. But this thing will be like more efficient than just the scalar functions. The reason here is like you will be able to use the more low-level Pinot APIs. So pretty much like for all the transform functions, you're going to implement this transform function interface. This interface, it has like all those function names, how to init the function, and this result metadata is important because it will give, it will define like how the function response metadata of the results, right? So what kind of like data type, if it's like if you go to here, the function, it has like, well, the data type, it can be like string. And if it's a single value or multi-value column, or if it has a dictionary or not. So all those things will be passed to the next functional operator to process. If you think of like you have a chain kind of like transform function, then all this information will be used by the author functions for this. So this is like the very basic interface. However, a lot of like so we already implement something called based transform functions, which is kind of like being used way more popular, and there'll be like majority of the normal transfer functions are based on this kind of implementation. Is you can just extend this class. For example, if I want to do very simple ones, I can say just here addition. This is just a plus, right? So just here, so although we already have like the scalar functions for plus or add, but with the transform function, we will be able to do things faster. If you look at here, from the init perspective, I'll be able to tell like this will be like multiple arguments of like the transform functions. You can think of like if I want to do add, right? So on the line, it will be multiple transform functions giving me the value to be added here, which means uh, from here, I would just, for example, I'll define my result data type is always a double because I don't want to handle anything related to like type conversion. I will just promote everything, even if it's like int plus int. I can say, okay, the result is double. So the only caveat here is like you need to handle if it's a big decimal or it's a really double, right? So the result could be different. And and then on the line, if I'm like uh, implementing these transform functions, so everything is based on this like a value block. For the value block is nothing but just like uh, implementing like it's like a block of the data to be like transformed or like modified. If you think of here, I will be able to tell, okay, this is my value block size with this length, and then I will be able to do something like a transform function or like a for loop to do all those kind of value add for all those kind of like multiple like transform functions together. So here, because my result type is either double or big decimal, that's why I'll just implement like two methods. It's like transform to double values. It means that this operator or this function will generate it will consume multiple value blocks and generate a double blocks a block with like an array of the double values. Here is a double array, and similar if it's like if the return type will be like big decimal. For example, your input data will be big decimal, then my result will be big decimal array as well. So this is like a very simple example of this transform functions. And after you implement this kind of thing, you also need to register this one in code, which means it's like from here in this transform function factory, you actually need to define your implementation of this kind of like all the built-in transform functions here. For example, this is the add functions. You need to uh, put some enum here for your add functions, and then uh, you need to get back and add this is your class mapping so that when you run these transform functions, I mean, when you write these functions in your SQL query, Pinot will be understand, okay, this is like transform functions, so it will use transform functions first.
Hey, Xiang,
Next thing I'm going,
time check.
time check, okay, sorry. Yeah, because I started late, so I'll just
Yeah,
getting bit more
you've
time.
got a couple more
Yeah,
minutes.
yeah, yeah, yeah. So the next thing here is about the aggregation functions. This is like a similar to transform functions. However, for aggregation functions, um, from the definition perspective, the interface part, we have something called the intermediate results, which will be like um, the aggregated the intermediate aggregated results coming from segment. And the final result will be something like getting returned to the from the broker. That's like the end user kind of like seeing result. For example, for hyperlog log, right? Hyperlog log for hyperlog log, all the intermediate results will be still the hyperlog log object. It can be some bytes However, for the final result, it will actually be something like either integer or a long because that's the estimated cardinality value that I want to get. So, hmm, so for example, I should just coming from here. So one thing here is like we also similar to transfer function, we also have like some good abstracted classes implemented. One thing is called this base single input aggregation functions. I would suggest to read all those kind of implementations. For example, there will be something called super simple function called sum aggregation, right? So from the aggregation function perspective, we just need to implement three things. So four things. One is like how we do the batch aggregation logic. From the sum perspective, what we need to do here is for different type of the value from the block side, I will just do the int and add everything back into just one value. And also I need to handle how we implementing the group by logic, right? So for the group by things, we need to like handle for each group. I need to grab the value from the group key and then do the add. If the group key doesn't exist, I'll need to create the group and set back into the group by result holder. The next thing here is like we will need to use this aggregation results holder for all the intermediate results. If you look at here, we do have something called the get intermediate results column type. For some kind of functions, it will be simple because your intermediate and the final results are the same. And similar to this thing, you get the final results column type. And another thing is like you need to be able to implement how you want to merge the intermediate results and how you want to merge and extract the final results coming from these intermediate results. So that's pretty much like how you are going to implement the aggregation functions. And the last thing here is like all the aggregation functions need to be registered here. It's under the aggregation function factory. It's pretty much similar. For all the simple aggregation functions, you have like this kind of like count, min, max, sum, list, agg, all those kind of functions are listed here. If you implement your own kind of aggregation functions, you need to register here and kind of like compile and build your Pinot binary yourself. We are kind of like working on how to like abstract this kind of logic and make it simpler to be like super pluggable with like drop jar kind of solutions. However, that will be need some like more time to do it. That's pretty much for my talk today. And let me know for any questions.
Hey, Xiang, we were just talking about any potential limitations. I think Yash was pointing out, the one-to-one
Mm-hmm.
limitation on scalar functions. Is that
Yes.
correct?
Yeah, I mean, this is like kind of like how you are going to run SQL, right? So there will be like all the mapping kind of relationship will be like either one-to-one mapping. It's like a one row map to one row after your transformation, right? That's called transform function. And then there will be like unrow into one row that will be called something like aggregation functions. And there will also be something like unrows to probably like m rows. That would be something like window functions, or there could be like more kind of more complicated kind of functions, or it's more
Transformation
like
functions.
processes kind of, yeah.
For,
So all those things like we're also implementing. For example, like window functions right now, it's also being like being modeled as like aggregation functions in certain cases. And however, the results will be actually more in terms of like uh, kind of like when we decode the results, it will be like a huge block kind of growth from the aggregation function perspective. Yeah, I think the main thing here is like we want to first make the simple things to be super easy to use. Hence that was kind of like scalar function annotation. For the aggregation functions and transform functions, the main purpose of the philosophy here is like we want this thing to be super fast, which means that we need to be able to access some very low API to ensure all the operations are like very efficient.
But around like input and side of the parameters and the output, right? Are we talking about,
Mm,
all of the types that are, at our
yeah.
disposal, like the basic types, and I think some of the more complex
Mm,
types that could be used for developing new scalar functions, for example.
Oh, you mean something like a reload kind of
Like
function,
your
something like
example was like you had one column as a parameter for a scalar functions
yeah,
and using simple types, right? I'm
yeah.
thinking about more like complex scenarios that maybe take multiple parameters or use different like data types for return values.
Yeah, I think for we do have scalar functions for like multiple arguments. It's like if you define the scalar functions with multiple arguments, then it means that your when you run your SQL query, you need to give multiple fields, right? So, however, it's not as simple as like Java functions or something like method is like you can reload the thing. For example, you can say, okay, I want to add column A and column B, and I probably can also do like add column A, B, C. That's not possible. You need to write it as like add A and B, and then there'll be another add on top of this add function, and then add C. Right. So a lot of like usage will be like limited to like uh, fix the number of the arguments. So that's kind of like by design.
And all of these functions still are run within the context of like the plan, right? Like there's um, within the
Hmm.
scope of that particular one query
Yeah,
that's
yeah,
it's kind of
especially
sandboxed to that.
for right, yeah, especially for the multi-stage query engine, we do enforce like more like a strong type check and also the number of the arguments check. So it will be very so comparing to like the V1 kind of like scat-gather kind of query engine, V2 engine will be much more like strict in terms of like handling all those like function registry and running the query with different types. Yeah, also for like a lot of functions like string functions, like uh, like many kind of scalar functions, we're actually been lacking functionalities. So here, I would also suggest people to start contributing more. Here, if you look at, I do have like many function definitions here. For example, you want to say like, oh, this is mass functions, and you will see like here are all the URL functions on the right side, right? So all those things are like very simple scalar functions. And if you do feel that a lot of functions are very useful, feel free to submit the PR and add it into the main Pinot code base. For example, like the JSON functions. We do have like scalar functions, they're like JSON paths, those kind of extracting values. And for hash functions, I know this is will be like very limited, uh, but we do have like all the like murmur hash, city hash. There will be like many kind of different way of like you have x64 bits, 32 bits, those kind of functions. Because we have a lot of like crypto kind of use cases as well. So all those things are like very you're very welcome to like contribute to Pinot. Okay, so I think we're at the time, and we'll let Yash to start the next section.
Sure, I'll just share my screen. All right. My screen is visible, right?
Yes, Luke, go ahead.
Awesome, thanks. Hey everyone, my name is Yash. I'm a software engineer at Startree. I'm also a commenter on the open source Apache Pinot project, and I've been working on its query engine for over a year now. I'll be talking about optimizing queries in Apache Pinot today. So let's first take a look at the agenda for this session. We'll start off with a brief introduction, including an overview of the query engines in Pinot. What do the optimization strategies actually involve? Indexes in Pinot and data shuffling. So we'll also be diving into the actual indexation strategies that Pinot uses to speed up these queries. And then we'll finally talk about optimizing join queries by reducing data shuffling using smart data layouts. All right, without further ado, let's just jump into the introduction. Firstly, how Pinot stores and queries data. So, like most other databases, Pinot stores tables. These tables are divided into disjunct segments, which are the atomic storage unit in Pinot. And tables in Pinot can actually be partitioned on certain columns. And servers are the nodes in the Pinot cluster that actually store these segments. And each segment can be actually stored in more than one server since Pinot supports replication for high availability as well as for scaling out query workloads horizontally. And brokers are the components in a Pinot cluster that receive queries and compute query plans using sets of servers and segments. So we'll see what that looks like through each query engine. Yeah, coming to the query engines, Pinot has two query engines. Firstly, we have the single stage query engine, which was Pinot's original engine for super fast real-time analytics at scale. And this has support for a basic subset of SQL, including projections, transformations, aggregations, group bys, UDFs that Xiang just talked about, etc. However, this simple query engine, though super powerful and fast, does not support joins or window functions or subqueries and other more complex SQL constructs. The reason for this, and also the reason it is so fast, is its simple scatter gather model. So here, brokers receive queries, compute a simple but optimized query plan, distribute the plan to servers, which do the actual request processing on the segments, before sending the response back to the broker. The broker reduces or collects all the responses from all these servers into a final response before sending back this final response to the client. So we also have a concept of pruners on brokers and servers that actually reduce the amount of data that need to be read for each query. And servers use indexes to further reduce the actual amount of data read from disk. We'll see this in more detail shortly. The multi-stage query engine was introduced to Pinot in Apache Pinot 1.0 a couple of years ago, primarily to support query time joins. It also added support for the full gamut of SQL functionality, including window functions, subqueries, common table expressions, and so much more. In this engine, queries are divided into different scatter-gather stages that form a tree, and leaves in this stage tree. So the leaf stages are actually wrappers around a single stage query engine. And this is where data is actually read from disk and also where the indexes are leveraged in the multi-stage engine. So the brokers optimize the distribution and assign stages and partitions to workers on the servers based on the query parallelism. So that's a bunch of jargon, but most importantly, what you need to keep in mind is that data is shuffled between these stages, either using gRPC or in memory, depending on whether the stages are on the same server or separate servers. So of course, ideally, we'd want to avoid shuffling data through gRPC because that's going to add network overhead. So let's talk about optimizations. So the bottleneck for most database query engines is I/O. And the main goal for most query optimizations is to reduce the amount of I/O needed to answer a query. So at a segment level, Pinot does this through its various indexation techniques and reduces the amount of data that we actually need to read from disk in order to serve a query. These techniques are applicable in both the single stage engine and the multi-stage engine. As I pointed out, the multi-stage engine simply wraps over the single stage engine in its leaf stages. So that's where the indexation techniques come into the picture. In the multi-stage engine, particularly in large distributed join queries, the bottleneck shifts to the network overhead of shuffling data between stages. Here, smart join strategies exploiting optimal data distribution like co-located joins come into the picture. Before we talk about the indexation and co-location joins, we'll take a look at a few super simple yet powerful optimization techniques that are applied at the server and broker level. So here, using the pruners we talked about earlier, we reduce I/O by actually reducing the total number of segments that need to be processed. So at the broker level, we can use two strategies. One is time-based pruning and another is partition-based pruning. So in time-based pruning, if a query has a time filter, we can simply reduce the number of servers that we fan out the query to based on metadata that the broker maintains about the time ranges that each server contains for a table. Similarly, for partition-based pruning, we can eliminate a number of servers in the broker itself, in the query plan, by simply limiting our query fan out to the servers that actually contain segments from the partitions that we are querying based on the query filters. At the server level, we apply another level of pruning. So here we use Bloom filters and as well as min-max value-based pruning. So each segment will have some metadata that maintains for each column in that segment, the min and max value. And we can use that to simply reduce the number of segments that we need to read based on the query filters. All right, let's talk about Pinot's index optimizations next. So we'll start off by looking into a couple of Pinot's simple but powerful indexes. The inverted index stores a mapping from unique values for a column in a segment within a segment to a bitmap of the document IDs or rows in that segment that have that value. So the bitmap used here is a roaring bitmap. These are highly compressed and super space efficient, yet extremely performant. So as you can see in this illustration, so let's say this is an index within a segment. There are 5 unique values. Each of these unique values will have an entry, which points to a bitmap of documents that actually contain that value. Documents are basically rows in that segment. So this index can actually massively speed up queries using filter predicates like equals, in, etc. And we'll take a look at some numbers soon. This index is not recommended for columns with extremely high cardinalities though, with the obvious caveat that the storage footprint would blow up in this case because there'd be a huge number of unique values and each of these would have a corresponding bitmap of doc IDs. So in that case, the space-time trade-off usually would not be worth it. In those cases, we can actually use something called a range index. So this is a variant of an inverted index, and it's very similar to the inverted index. Here, instead of storing mappings from unique values to bitmaps containing the document IDs, we store mappings from ranges of values to bitmaps containing the document IDs. And these ranges are of course configurable, although Pinot will try to impute smart defaults. And this index can massively speed up queries using range filter predicates, but also equality predicates since less data would need to be scanned. So for instance, if you are using a range filter, we can simply look up the index for the corresponding ranges. If you're using an equality predicate, we can look up the corresponding range and then we'll need to read less number of documents than the total number of documents. So this index is great for dictionary encoded columns or raw numeric columns with large cardinalities. Let's take a look at a simple example. I'm not sure this is visible, but essentially what we have here is a simple query, a select count star query with a couple of filters. So these filters are initially on columns that don't have any indexes, And the explain plan will show that we have a number of filter full scans, or essentially we're reading the entire column from the segment. Remember that Pinot uses columnar storage, so each segment actually contains data in a columnar format for each column. And let's execute the query. So the query actually ran in 230 milliseconds, which is not bad, but we can do much better. And we have in the order of 100 million rows in this table. So these are about medium-sized tables, not too large, not tiny either, though. We'll go ahead and add our indexes. So we have two inverted indexes and a range index on the columns that we want to query. And our explain plan will show that we're actually using the range index and the inverted index and not having to scan the entire column for the query. And if we execute the query again after adding the indexes, we can see that it executed in just 9 milliseconds. So it went down from 230 to 9 milliseconds. And that's purely because we had less IO, less disk IO. We read less data from disk thanks to our inverted and range indexes. So here we combined index-based filters using ANDs in the query. So how does that actually work? Well, since we have these bitmaps containing doc IDs, we simply perform extremely efficient bitwise operations on these bitmaps to get the final result. So we can use bitwise and, bitwise or, corresponding to the actual clauses in the SQL query, and we'll get a final bitmap containing the documents that match all the filters. Additionally, for count star, we have another optimization that allows us to skip scanning the final selected documents or rows altogether. We can simply count the number of set bits in the bitmap to get our result. So that's as simple as that. Some of the other indexes we have include this famous star tree index. So this is the only multi-column index that Pinot has. So this is like a segment level index instead of a per column index. And it's used to speed up aggregation and group by queries. It essentially offers a configurable space-time trade-off and uses pre-aggregation to massively reduce the number of rows that need to be read to serve an aggregation query. It's a super interesting index, but it's too big for the talk, and it's a topic good enough for an entire talk by itself. I'll link some resources that already go into depth here. We also have a JSON index that can apply to JSON string columns to accelerate value lookups and for filters on the column. We have text index based on Lucene for phrase search, term search, regex search. We have a timestamp index for efficient timestamp operations. We have a geospatial index. We have a vector index that supports similarity search using the HNSW algorithm and many more. And interestingly, Pinot, even though it comes with a ton of indexes out of the box, also supports plugging indexes. So similar to how we can plug in UDFs, we also support plugging in custom indexes based on your query patterns and requirements. So we'll quickly take a look at some numbers. So the power of indexes, right? What other databases try, and while they try and do the same work faster, we work differently. And you can see that ends up scaling really well, both in terms of size of the data as well as concurrency or query throughput, because Pinot basically can run a lot more queries with a limited number of resources in terms of hardware or infra footprint. So actual concrete numbers that we saw in some queries. So you can see the query latency is the y-axis, and we have basically with and without various indexes. And you can see some crazy improvements. Like for example, the star tree index without the index, or just a raw query, a query that took 31 seconds went down all the way to 50 milliseconds with the star tree index. So we get these amazing results through our powerful indexes because we massively reduce the amount of IO that each query requires. So some more great numbers here in terms of QPS throughput as well as latency. So we see both the throughput increasing, max throughput supported increasing, and at the same time, we see the query latency decreasing with the use of these indexes. All right, so bit of a change of pace. We looked at segment level optimization in the form of indexes, and these are super powerful for simple queries. But what about distributed joins and other complex query patterns with the multi-stage engine? So while we still leverage the power of indexes to reduce disk I/O, but with distributed joins comes another I/O bottleneck, that is network I/O for data shuffle. Let's take a look quickly at how that works and how we can optimize that as well. So in order to execute a join, all the rows of the tables to be joined need to be in the same place. So in classical databases like Postgres, this is not a problem as there's usually a single server or all servers have all the data. But in distributed databases like Pinot, where rows of the tables are distributed across servers, data needs to be shuffled between servers in the general case in order to execute a join. This data shuffle is expensive and can be a bottleneck for the query performance. So the absolute most simple way to execute a distributed join would be to move all the data into a single server where we would then execute the join. And here the rows shuffled would be less than equal to or of the order of the total number of rows across both the tables. Let's take a look at this example where we have three servers, two tables A and B that need to be joined with segments spread across the three servers. So here, let's say we choose server 2 to execute the join. We'll send across all our rows for both the tables into that server. Then we'll actually execute the join before sending the final result to the broker and to the client. While this works, this is not scalable because we are going to be creating a huge bottleneck in the single server that is going to be collecting all the rows across multiple tables that need to be joined. So what we actually do instead is create virtual partitions at query time. Let's see what that looks like. So for equijoins, so for instance, on a.some_call equal to b.some_call. So if in this join condition, it's possible to assign a partition function to each table on both sides of the join that guarantees that if the partition value for the two columns is equal, then the two column values will also be equal. So the most common case is to simply use a hash function as a partition function. And the corollary of this property is that rows that end up in different servers after the partition-based shuffling, they never needed to be joined in the first place because of the property of the partition function or the hash function. So here as well, the number of rows shuffled is equal to is bounded by the total number of rows in both the tables. But we see that this is a lot more scalable because we are not creating a bottleneck on a single server. So for instance, let's say we create these three partitions for each of the tables, P0, P1, and P2. Then for each row in all the segments of A, we apply the partition function. If the value for the partition function output is, let's say, 0, the row will be sent to 0. Similarly, if it's 1 or 2, it will be sent across. So here, for the rows that are being sent to a virtual partition in the same server, that will involve in-memory data shuffle. For the rows that are going across servers, that's going to be through gRPC, like we talked about earlier. So here, after we do the data shuffle and send the rows to their respective virtual partitions, we execute joins on all the servers that had the virtual partitions, and then we collect the results into the final join output that is outputted to the client through the broker. Okay, so while that works, that's still not great because we are shuffling a bunch of data over the network, and we said that we wanted to avoid that because that creates a huge I/O bottleneck and overhead that slows down queries. So this is where co-located joins come in. It's a strategy that Pinot can use to execute joins without shuffling data between servers when these conditions are met. So both the tables need to be partitioned. Remember that tables themselves can be partitioned across servers on certain columns. The partition function and the actual partitions that are outputted for these tables need to be the same, and they need to be co-located, or essentially these partitions need to be placed on the same servers, and Pinot supports some table configurations to ensure that two tables are co-located. So based on your query patterns, you would configure these tables to be co-located so that you can employ the co-located join strategy. And of course, this can only be used for equijoins because that is only when we can use the partition-based strategy in joins. So here, if we do have this all these conditions being met where two tables are co-located, so we can execute the co-located join strategy. And here, since we have no data shuffle over the network, the join query will be sped up massively by 1 or even 2 orders of magnitude. So let's just see what that looks like. So we'll be creating our virtual partitions again, but this time the virtual partitions will essentially correspond 1:1 to the actual partitions or actual physical partitions on the servers. So again, here we'll be executing our joins after we, well, don't shuffle data, but we just collect the rows from segments by just moving data in memory. We'll be executing our joins and collecting the final result. And yeah, there we have a distributed join executed across servers without actually shuffling any data. The only slight disadvantage of the strategy is that it may not use as many servers as other techniques. So for example, the same query using query time partitions may actually use 3 servers to execute the join, while in this case, Pinot can only use server 3 and 2. Server 1 can't be used because it doesn't have segments of table B. So yeah, let's just take a look at some numbers again. So let's take this join query as an example. The data set is about 10 terabytes across 16 servers. It's a fairly simple query. It's a left join with a single equality based join condition. And we have a filter, we have group bys, we have an order by. And the number of records in the left table was about 6 billion, with number of records post filter being 1 billion. And the number of records in the right table was about 130 million. And we apply a number of optimizations. So first, the baseline is taken with no optimizations in scan or data layout, and the query latency was a whopping 39 seconds. Next, we have predicate pushed out, where we actually push the filter into the table scan and leverage the power of indexes. So instead of applying this filter post join, we apply it the table scan pre join, and we actually use an index in an inverted index. And that's going to see a significant reduction in both the data being scanned as well as the work done for the join. And hence latency goes down from 39 to 4.5 seconds. Next, we have collocation or partition aware joins. We partition the tables on the join key and collocate the partitions. So this also prunes out segments that are not relevant to the join and reduce the data shuffle, further reducing latency. So now we have the latency down to 3.3 seconds. And more importantly, since we no longer have data shuffle, the the amount of garbage collection being done, the number of allocations we have, the amount of memory being allocated reduces massively, because we don't no longer need to serialize and deserialize the data as well. So what this is going to do is actually make the joins much more scalable. You can support a much higher throughput of join queries. And finally, we have the big hammer of increasing parallelism by actually using the same number of servers, but with 32 cores each instead of 4 cores each server. The latency comes down to sub-seconds, which was our original goal. So we have this join query executing in 0.5 seconds. So given there's a cost involved to this, of course, we chose to keep this as the last iteration so users can choose the trade-off depending on the latency SLA. All right, that's all I had. I can take questions. Oh, I see some questions in the chat. Let me just take a look. Sorry,
Yeah, I'd
just give me
say
a sec.
that a lot of optimizations are like pretty specific and requires like users to have really like a knowledge to analyze all the compute processes, right? So do you have any plan to maybe like for example, giving the suggestions on like how to optimize or if possible, maybe like try out some GenAI kind of solutions to help optimizing this kind of things like automatically. Uh, what do you think?
That's an interesting one, but actually, uh, so what I talked about co-located joins in older versions of Pinot actually required user-provided query hints to let the planner know that the tables are co-located. But in newer versions of Pinot, the planner will actually be able to detect that automatically, and users will no longer need to provide explicit hints. So that's the way we are going forward to actually be able to automatically apply optimizations as and when we detect them. In terms of other optimizations, I think, yeah, we do need to do a better job as a community to actually, collate all this information and have it centrally so that maybe users can use AI to actually get this stuff. Right now, I think this knowledge is spread across various places and we don't have it in a centralized place. Maybe the first step could be starting a new documentation page on the OSS Apache Pinot
Mm.
doc website just about optimizing queries where we collect all known strategies across various users of Pinot for optimizing various kinds of queries. I think that could be a good initiative.
Sure. Yeah, as well, like for a lot of optimizations, it may require the like data reshuffle, those kind of things. I think we also probably need a better story in terms of like simplify how to for example, reshuffle the data and re-ingest the data, or like
Mhm.
which is like could like easily or help user to have a way of like optimizing the query, because the the query optimization requires the layout of the new kind of like data layout, right? So
Yeah, that's
yeah.
right.
I think right now, like we have, the query plan, the explain plan option, and there's been some relatively recent enhancements to like the visualization of the plan within
Yep.
the controller UI, and I think there's some additional work being done there
Mhm.
to better improve like the readability of the plan.
That's right. So we actually added visualization for query stats as well. So when you actually execute a multi-stage query, you get stats in the form of a tree. Earlier, it was just outputted as a JSON, which was super difficult to actually analyze and find bottlenecks. So the JSON's based stats are now being visualized into a tree, which will correspond to various operators, and each node in the tree will contain stats for that operator, including the number of rows it outputted, the number of bytes it processed, the amount of time it took to process, of course. And you can very easily find the bottleneck in a query through this tree-based stats in a multi-stage query. And yeah, we are working on further optimizing and enhancing that as well to make it super simple to find bottlenecks and optimize queries.
That's in 1.3, correct? The,
No, yeah, so actually, I believe the initial version is, but we have added a few more enhancements which will be in the upcoming 1.4 release. Yep, that's it from me. I think if there's no more questions, we can probably end for today.
Yeah, so thanks everyone for joining the call, and we will also share the video recording later for people references, and also we will upload this one to the YouTube channel as well. Okay, yeah,
and
so thanks everyone for
we have
joining, and we will schedule the next call, right? Robert, you have some other schedule
Yeah,
or
I just
agenda?
we just wanted to ask folks to complete that survey. I dropped a link in the chat. We have a
Yeah,
Pinot contributor calls channel, and we have some topics already planned for August and the rest of the year. So keep an eye
sounds
out for
good.
those things.
Yeah, cool. Thanks everyone, and we'll see you in 2 months.